Swayam Prabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 36 on the ongoing series on mechanical measurements. It also is the beginning of the module 4, which basically deals with some specific topics which are of interest in measurement science. The things we will be interested in doing will be the thermo-physical properties of materials. Then we will look at radiation properties of surfaces. We will also look at the measurement of torque, power and such quantities which form a part of power sources. Then we will also look at the measurement of vibration and noise. These are all some special topics which I would like to take here in this particular module. The first topic I am going to look at is the measurement of thermo-physical properties. It is a very vast area, and necessarily we have to restrict to a few important thermo-physical properties. In my opinion, these are the ones which require a little bit of understanding, and the measurements are somewhat involved, and therefore I have included them in the presentation in this lecture and the subsequent lectures to come. The quantities which will be of interest in thermal science basically are the properties of materials like thermal conductivity, which of course could be for any of the states of matter, solid, liquid or gas, and each one of them has a specific problem attached with them, and therefore we will certainly look at the measurement of thermal conductivity of various materials in the three states of matter. We will be interested in the thermal capacity or the heat capacity of the materials, and that will be dealt with subsequently. And one of the important things which we require when we talk about power plants, either based on fossil fuels or either gases and liquid fuels and so on, is the measurement of calorific value of fuels. So we will deal with one or two examples of how to measure the calorific value. Basically the heat capacity and the calorific value of fuels are basically of the same type of measurements. And then of course we will look at viscosity of fluids. Again, they can be different states of matter like solid, liquids and gases. Of course, if one would like to completely look at all the thermo-physical properties, there are many other interesting properties like specific gravity, density, thermal diffusivity, then molecular diffusivity and so on. So it is a never ending topic, it is a very vast subject, and therefore what I have done is to select only those which are of immediate importance and which will bring out the features which are common to all these measurements. Therefore the properties I am going to consider only representative, but they cover more or less all the nuances which you will find when you want to measure any of the thermo-physical properties other than the ones which I have listed here. The first thing I am going to look at is look at the measurement of thermal conductivity, and of course we will go on to the other topics as we go along. Thermal conductivity, as you very well know, is a fundamental quantity of interest whenever we talk about heat transfer in any material, whether it is liquid, gas or solid. And of course, when you talk about conduction, only conduction heat transfer taking place, it is only in the case of a solid, assuming that of course the solid is stationary and there is no possibility of much movement in the macroscopic sense. So, solid is the only case where thermal conduction can be actually studied in great detail. In the case of both liquids and gases, immediately when you have a temperature gradient in the system, there can be some amount of movement because of density changes or density differences, and therefore, we have bulk motion. So, the main problem which we will find, which we will have to address when we talk about the measurement of thermal conductivity of liquids and gases is the mechanism or how we are going to suppress these fluid motions, how we are going to minimize the effect of convection, so that we can study the conductivity or conduction phenomena in isolation. So, that will be the major difficulty. So, the various techniques available can be classified broadly into two broad categories. We call them the steady state methods, and of course, we have the unsteady or transient techniques. Steady state methods generally take a lot of time in terms of the time that is required to bring the process from the beginning to the steady state and maintain in the system in the steady state. So, the steady state methods are usually time consuming, and some of these methods will require days of time, not even hours. Several days will require for the technique to come to the steady state condition. Then in the unsteady method, the advantage of course is that the entire experiment is conducted very fast, in a very few, maybe in a few milliseconds or few seconds or within a few minutes, and therefore, there are some important advantages with the unsteady method. But unsteady methods are more expensive in terms of the equipment required generally, and therefore, we are going to discuss only one or two methods as we go along. Among the steady state methods for the measurement of thermal conductivity, we have the most important one is the guarded hot plate method, which is considered the primary standard for the measurement of thermal conductivity. We can use it for both for the case of solids and liquids, and I will demonstrate, I will show how it is done. Then we have what is called the radial heat flow apparatus, which uses a very small gap between two cylinders, and the specimen either in the form of a liquid or gas is taken in the gap, and we allow heat transfer to take place across the gap under a temperature difference. And in fact, there is one way of suppressing any convection phenomena taking place or convection taking place within the sample. The third method I am going to discuss is the thermal conductivity comparator, which will be with respect to the measurement of thermal conductivity of solids. So, the first topic I am going to look at is the guarded hot plate method, and then I will also tell how it is going to be useful for both solids and liquids, and then we will look at a radial heat flow apparatus, which will be useful for both liquids and gases, and then we will go on to thermal conductivity comparator. It is possible, and that in this lecture I may be able to complete only the first two here, and then of course we will go on to the other ones in the subsequent lecture. Before we take a look at the details, let me just give a brief background on the thermal conductivity, so that we understand what is required. So, we will look at the Fourier law of heat conduction, which is the basic law which is going to be used in conduction heat transfer. So, Fourier law of heat conduction, which states that the heat flux is a linear function of the temperature gradient. Of the temperature gradient. Of course, temperature is a scalar quantity, and the temperature gradient of course will be a vector quantity, and heat flux is also a vector quantity because it has got both a magnitude and a direction. And what is done in practice is not to consider heat transfer in an arbitrary temperature field, but in an one dimensional temperature field. So, what we will do is we will confine to heat conduction in one direction or in one dimension, in one dimension or in a single dimension. What does it mean? It means that the temperature is a function of only one space coordinate, and we can call it x or y or z, whatever we want, and the temperature field varies only with respect to one coordinate, which is x, for example. So, if I look at the Fourier law of heat conduction, which is now written for a single direction. So, I will just show it by having a material medium in the form of a slab. So, we will say this is a slab, and we have the direction of heat transfer indicated by this. So, we will say the heat flux is in the direction x direction. So, the temperature will vary from the left to right. So, if the temperature is something here, so it will vary like that. So, this is T 0, and we will say this is T L, and the thickness of the slab is L. So, we will write the equation as Q in the x direction is given by K, the thermal conductivity of the solid or the medium, multiplied by T naught minus T L divided by L, and you can immediately see that the temperature gradient has become T naught minus T L divided by L is the temperature gradient, and K is the factor thermal conductivity which is to be determined. Qx is the heat flux by conduction. So, we will see the units are going to be watts per square meter here, rate at which heat is transferred per unit area per unit time. The rate is transferred per unit area, that means that the amount of energy crossing per unit time and unit area of the slab. T naught and T L are the temperatures at the left and the right end of the slab, and L is the thickness of the slab. Of course, I am assuming that this is a slowly varying function of T, or slowly varying with T, or maybe not at all varying with T. If I make sure that the temperature difference T naught minus T L, the temperature difference across the slab is very small, I can say that the thermal conductivity I am going to determine is actually at the mean temperature of the solid or the medium, which is T naught plus T L by 2, and it is very close to the difference. T naught minus T L is very small compared to the mean value. So, I can say that if T naught minus T L is very small compared to T naught plus T L, then I can assume that thermal conductivity is the thermal conductivity at the average value. So, K is nothing but the thermal conductivity mean value of K, of the thermal conductivity. If I maintain a temperature difference of the order of 5 degrees, for example, between the two ends of this particular slab material, then it is close enough to being at the mean value, with the perturbation or the change with respect to mean value is only plus or minus 2 degrees or 3 degrees. So, it will satisfy the requirement that the thermal conductivity I am going to determine is at the mean value. Why I am talking about this is, if we have a medium whose thermal conductivity varies significantly with temperature, I have to conduct the experiment such that at any heating level or any mean value of the temperature, the perturbation or the variation of the temperature across the slab should be small compared to the mean temperature of the solid. That is how you have to actually maintain the conditions, so that thermal conductivity can be obtained as a point function or as a function of temperature, where the temperature is identified with the mean value. So, with this background, let us look at what one has to do in any experiment where I want to measure the thermal conductivity. One, I have to measure Qx or the heat flux. I have to measure the temperature T naught, TL, the two temperatures have to be maintained, measured, and I have to measure the length or the thickness of the solid or the medium in this particular case. So, I have to do 4 measurements Q, T0, TL and L. 4 measurements are required before I can obtain the value of K. Actually, what I am going to do is I am going to write it in the following way. I will say that K is equal to Q L divided by T naught minus T L, that is the expression for the thermal conductivity. It will require the measurement of Q, L, T naught and T L. 4 quantities are required. 4 quantities are measured. Of course, in practice the temperature is measured using, for example, thermocouples can be used. The length has to be measured using a accurate length measuring instrument. The Q sometimes is the most difficult to measure, because Q itself is the total heat transferred, divided by the area through which the heat is transferred. The major thing one has to remember is that we have to maintain an one dimensional temperature field. That means that we have to see that the temperature varies only with respect to x, and there is no significant temperature variation in this direction. So, the transverse direction there should be no significant temperature variation, only variation should be along this direction. That will be guaranteed only if Q is truly in the direction which is shown. There cannot be any heat loss in a transverse direction. Of course, if we have an infinitely large slab, it is easy to maintain that. In practice, an infinitely large slab is not possible, so we always have a finite size sample. When the sample size is finite, it is difficult to maintain the one dimensional heat transfer or the heat transfer in a direction as is shown here. So, that is the major thing which we have to look at. So, how to obtain heat transfer in a particular direction, in one dimensional, in one particular direction without any losses in the transverse direction. So, that is the major thing one has to look at. Let us look at the principles involved in doing that, and that I will try to do with the guarded hot plate apparatus. I will indicate how it is done. Before we do that, let me just recapitulate or summarize what I have talked about. So, the first goal is to achieve one dimensional temperature field within the medium. This is the first thing one has to do. So, I have to achieve somehow one dimensional temperature field within the medium. I have to measure the heat flux, that means that the amount of heat transferred per unit area in unit time. I have to measure the temperature gradient, either by measuring the temperatures individually and the length separately, and then taking the ratio. I have to, using these 4 quantities as I mentioned earlier, Q, L, T naught and T L, I will be able to estimate the thermal conductivity. The additional problems when we come to liquids and gases is how are we going to suppress convection. In the case of solids, the advantage is that there is no possibility of any movement of the solid in the macroscopic sense of the term, and therefore, I do not have to worry about the suppression of convection. In the case of suppression of convection, either I can use very short time for the experiment as in the unsteady or transient methods, or I have to take special precautions so that these movements are not going to be present. Finally, we have to look at the parasitic losses. Even though I am saying that we will achieve one dimensional temperature field and so on, how closely are we able to do that? There will be always some parasitic losses. These have to be reduced or eliminated, or in the worst case we have to estimate what these losses are and account for these losses, so that the estimated value of thermal conductivity is of acceptable level of accuracy. So, let us look at one simple arrangement. In fact, earlier when we talked about the measurement of heat flux, we already looked at the concept of the guard, and if you recall from our discussion earlier, a guard heater is going to help in reducing the losses in a transverse direction, and therefore make the temperature field or the heat flux one directional or one dimensional. So, what we have done in the case of guarded hot plate apparatus, which is now for a solid sample, I am taking the example of a solid sample. I take two samples of identical size and thickness. There is sample, there is also sample, same material, same size, physical dimensions are the same. I am going to use them in the symmetric arrangement. So, I have a heater in between these two samples in a sandwich construction like this, and what I have done is I have got the what is called the main heater. The red symbol is for the main heater, and this blue color thing is the guard heater. I will explain this slightly more detail in the next slide. So, we have the sample on the two sides. The sample is going to occupy the entire width, which is the width of the or the size of the main heater plus the guard heater, and the sample is placed symmetrically on the top and the bottom, and what I am doing is the other surface of the sample at the top as well as the bottom are cooled by cold water, which is coming from a cooler, where the water comes in at cold water and go after taking out the heat which is transferred from the heater across the sample by conduction, it will remove the heat and go out, and similarly symmetrically on the bottom. And in order to further reduce any heat loss or heat transfer in the transverse direction, I am going to provide a large thickness of insulation of very low thermal conductivity. And in fact, this figure shows another quantity here, the force. I am applying a force in the direction shown like this, so that the contact between the sample and the hot plate as well as the cold plate here is guaranteed, so that there will be contact resistance will be very small. If there is contact resistance, the temperature we measure will show some, will also contain extra resistances due to the contact resistance, and therefore the method will not give you accurate value of the thermal conductivity. Therefore, in order to improve the material method, we can even apply a force, which is usually done by putting a screw and then tightening it, so that you get a sufficient pressure, so that the sample is in intimate contact with the surface of the heater as well as the cold plate. Now, we can easily see what we are trying to do. We are trying to introduce the heat at the center in the symmetric fashion. We can assume that if we put some Q watts into the heater, Q by 2 will go through the top sample, Q by 2 will go through the bottom sample, assuming that both of them are identical in shape and made of the same material. That means that same thermal conductivity. Half the heat will go from the sample from the up there, and the half will go from here, and of course the amount of heat we put in, I will be measuring using the amount of electrical heat supplied to the heaters. I also have the guard heater, which is surrounding the main heater, and what I will be doing is I will be supplying enough heat to the guard heater, so that in the gap between, there is a physical gap between the main heater and the guard heater, the delta T, the temperature difference is very small or equal to 0 in the case of ideal situation. There should be no temperature difference across the gap. If the temperature difference across the gap is 0, that means there is no heat loss from the main heater in the direction perpendicular to this axis. Okay, let us look at the typical construction of the guard and main heater. This sketch indicates what is happening. So, we have the main heater, which is something like 200 millimeters by 200 millimeters. This is the smallest size. You can in fact have much larger size if one wants to. In fact, it can be even 1 meter by 1 meter. In some situations, it is necessary to use very large sizes. Of course, if we use a large size, the large amount of heat has to be supplied, and also you require a very large sample and so on. So, the minimum is something like 200 millimeters by 200 millimeters, that is the main heater, and then you have a 50 millimeter wide guard heater all around the main heater with a small narrow gap. Of course, the gap I have shown here is too large. It is only for the sake of illustration I have shown that. The gap itself can be something like a couple of millimeters, 2 millimeters in this case. So, you have a 50 millimeter wide guard heater, then a 200 millimeter by 200 millimeter main heater, and we fix thermocouples as I have shown here. Across the gap I have got 2 thermocouples. These circles, closed circles are thermocouple junctions. I have 2 junctions here, 2 junctions here, 2 junctions here, and 2 junctions here, and the delta T, the temperature difference indicated by these 2 thermocouple pairs, junction pairs, must be ideally equal to 0. That means, in any experiment, in a particular experiment, I am going to dial up the amount of heat I am going to give to the main heater to a particular value. Then I will adjust the amount of heat supplied to the guard heater such that the delta T across this gap is going to be 0. So, I must have some kind of a controller which will monitor the delta T across this gap, and if the delta T goes up, it will reduce. If delta T goes down, it will, that is with respect to 0, if it is on one direction, it will, depending on the direction of the delta T, it will either increase or decrease the heat supplied to the guard heater, so that it comes back to delta T equal to 0. So, this is something which has to be built into the system. And the other point is that we are going to measure the temperature not at a single point, but we are going to measure temperature as I have shown here. For example, 8 temperatures are measured on one of the surfaces, and of course, there is another surface on the other side, okay, and also there is another surface on the cooled side. So, on each side I am going to have several thermocouple junctions like this, and then I am going to average them. In fact, I can do the averaging by simply connecting all of them, as we have seen earlier. If you connect them all in parallel, you will get the average value of the temperature, okay, because we are expecting that the temperature is more or less the same, uniform throughout, but there may be small perturbations, small changes. So, we would like to find out what is the mean temperature on this side, because for heat transfer calculation I need the mean temperature on this surface. Similarly, on the cold surface, the thermocouples usually are built in onto the heater, and they are not going to be attached to the sample. Sample is simply kept there, okay, and the sample, between the sample and the heater, you may give some kind of a surface treatment. You can make it very smooth and use some kind of a film of material of high thermal conductivity, so that the contact resistance is brought down. Therefore, the assumption we can make is that the temperature of the surface of the heater and the surface of the sample which is in contact with it are exactly the same, so that when I say T0 in the expression for thermal conductivity, we had T0. T0 corresponds to the temperature of the heater, and TL will correspond to the temperature of the cold surface, which will be the same as the temperature of the surface of the sample which is in contact with the cold surface. So, that is the reason why we have so many thermocouples, and we measure, as I indicated, delta T across this gap must be equal to 0, So, the guard heat input to the guard is adjusted such that delta T is 0, then you allow the entire thing to come to steady state, and it is generally it takes about 2 to 3 days for the steady state operation, steady state to be reached for a guarded heat plate apparatus. That means it is a very time consuming proposition. So, one single thermal conductivity measurement will take several days, maybe a week before we can get the numbers. So, let us look at the typical experimental conditions which we are going to have. The sample size 200 by 200 by 25, this is for the main the guard region, the main heater region, plus 50 mm you add on all these sides. So, actually the sample size will be 300 by 300, 200 plus another 50 on the either side. So, 300 by 300 by 25 mm. This is the main heater size only I have given here. Typical is this: the heat input is adjusted such that the temperature difference across the thickness of the specimen is roughly equal to 5 degrees. We do not want to have very large temperature difference across the thickness of the sample. The question now arises as to what do we do if we have a high thermal conductivity material, what do we do when the thermal conductivity of the material is very low. You can immediately say that from Fourier law, if the thermal conductivity is small, for a given heat transfer you require a larger temperature difference. Okay, you require a large temperature difference, or putting in another way, if thermal conductivity is small, for a given temperature difference the heat amount of heat input is small. So, if you want to have a 5 degree Kelvin, 5 degree Celsius difference across the thickness of the material, you have to adjust for a knowing roughly the thermal conductivity value of the material, we can find out what is the amount of heat I have to supply. That will vary depending on the material. The other condition other control I have is the thickness of the specimen. If the thermal conductivity is very small, I can take a smaller thickness for the sample, and if the thermal conductivity is large, I can take a slightly thicker material. So, the sample thickness can be adjusted, even though I have said 25 millimeter is the typical value, it could vary depending on the particular material whose thermal conductivity I am trying to measure. As indicated earlier, the temperature is averaged over the specimen area by having several thermocouples all parallel, so that you get the average value of the temperature. The contact resistance is reduced by suitable surface treatment for the hot plate as well as for the other surface by the application of force. The force is going to help in actually bringing out a good physical contact. A good physical contact coupled with this surface treatment will also mean that there is a good thermal contact. Therefore, the contact resistance can be reduced by this particular method. With this basic understanding, let us look at the example. This is example 41. So, we have a guarded hot plate apparatus which is used to measure the thermal conductivity of insulating material. The specimen thickness is 25 plus or minus 0.5 millimeter. So, now I am going to look at a typical case where the thickness is measured with plus or minus 0.5 mm precision, okay, 25 plus or minus 0.5 millimeter. The heat flux is measured within 1% and the nominal value has been obtained as 80 watts per square meter. This is the value. The temperature drop across the specimen under the steady state has been measured to be 5 plus or minus 0.2 degrees Celsius. Therefore, what I have done is all the measured values I have got the nominal value plus or minus the expected error in either 0.5 mm in the case of thickness, 1% in the case of the heat flux, and 0.2 plus or minus 0.2 degrees Celsius in the case of the temperature difference. So, determine the thermal conductivity of sample along with its uncertainty. So, I will work it out on the board. So, this is example 41. The heat flux is directly given. In practice, one would have to measure the heat the total heat supplied to the main heater divided by the area of the main heater to get the heat flux. In this case directly it is given, therefore, I will write down Q is given as 80 watts per square meter. This is the nominal value and the error is plus or minus 1% in brackets. Then I am given the thickness of the sample L, which is 0.025 25 millimeters is 0.025 meters plus or minus 0.0005 meters, 0.5 millimeters plus or minus 0.5 millimeters comes out to be plus or minus 0.0005 meters. I am writing everything in terms of SI units, and the delta T has been measured as 5 degrees centigrade plus or minus 0.2 degrees Celsius. It's a very simple problem. So, the nominal K I can calculate using the Fourier law of heat conduction, which is Q L by delta T. T naught minus T L is nothing but your delta T, and this will be 80 multiplied by 0.025 divided by 5. This comes to 0.4 watts per meter degree Celsius. This is the nominal value. It is very simple, straightforward. Plug into the expression and get the value of the thermal conductivity. The next part is to look at the error in K. I have to use the error propagation formula, which is familiar to us. We have dealt with in our first module when we are talking about estimation of errors in measured quantities. In this case, we are measuring Q, the heat transfer per unit area per unit time. We are measuring thickness and we are measuring also the delta T. All of them are prone to errors, and you can see that in this case, because K is related to the other quantities in terms of the product of Q and L divided by delta T, I can use logarithmic differentiation and obtain the value of delta K by K will be nothing but plus or minus square root of delta Q by Q whole squared plus delta L by L whole squared minus delta T by T whole squared. Of course, because it is square, this minus delta T by T is not going to make any difference. So, this I can just write the quantity. Delta Q is 1%. So, delta Q by Q is nothing but 0.01 whole square, 1% is 0.01. Delta L by L, I can substitute the values as 0.0005 divided by 0.025 whole square plus minus 0.2 divided by 5 whole square. All are ratios. So, when you do that, the entire thing comes to plus or minus 0.042. So, delta K by K equal to 0.042 or some 4.2%. This is a very typical value of error with when you use a guarded hot plate apparatus. According to normal standards which are specified for the guarded hot plate apparatus, about 5% plus or minus 5% is the expected uncertainty in the value of the measured thermal conductivity, and in this particular example it is within that particular value, within the plus or minus 5%. So, we can say this is plus or minus 4.2%. In fact, I can now specify the value of the thermal conductivity of the solid will be 0.4 plus or minus 4.2%. This is in watts per meter degree. So, I can specify it as 4.2% plus or minus 0.4 plus or minus 4.2%. That is the value which we will get using this particular method. So, what we have done is to look at the measurement of thermal conductivity of a solid using a guarded hot plate apparatus, and we have taken example and seen how to work it out and also see the type of expected error in this measurement. And if we recapitulate what we have already talked about when we are talking about measurement of temperature, measurement of heat flux and so on, the kind of numbers I have used in this particular example are typically the numbers which we discussed earlier. So, we know that in the case of measurement of temperature difference, plus or minus 0.2 degrees is a achievable value. Similarly, with respect to heat flux and with respect to the specimen thickness, also the plus or minus 0.5 millimeters is a very, very nice value. Actually, the reason why it is coming out plus or minus 0.5 is not because we are unable to measure the thickness, because many times the guarded hot plate apparatus is used for the measurement of the thermal conductivity of sample as received from the manufacturer. Okay, you just cut a small portion of the slab in the form, usually in the form of a slab or a plate, and you do not do much of a surface treatment or surface no treatment is given on the surface or no machining is done. Usually it is just taken as a slab as is obtained from the manufacturer. And many times we use the method. In this case, for example, the material has got a thermal conductivity of 0.4, which is characteristic of an insulating material, and usually this thickness is not very closely specified for such things, and therefore plus or minus 0.5 mm seems to be a reasonable number for this. It is not measurement related, it may be actually the material itself, the thickness does vary with this kind of a difference from position to position. Let us look at what we have to do if we want to use the guarded hot plate apparatus for a liquid sample. The main thing I have already mentioned is that when you use a liquid sample, there is the possibility of macroscopic movement of the liquid. Suppose I have a situation like this, I have a high temperature, let us say, as indicated here, you have a low temperature here, and suppose I have a liquid here. Normally the temperature, at a high temperature the density is smaller, and at low temperature the density is higher, and therefore the liquid will be lighter near the hot wall and it will tend to move up, and then of course the colder liquid will come downwards. So, therefore, you expect some kind of a motion like this, up and down motion. So, this is referred to as natural convection. And what is the consequence of this natural convection? The consequence is that the heat transfer is not simply by conduction, it is also because of this bulk motion, and therefore the heat transfer is actually much more than what would be if the heat transfer were by pure conduction alone. So, if I make an experiment with like I have shown here, with a high temperature at the bottom and a low temperature at the top, I am certainly not going to measure the thermal conductivity. I am measuring something which is not simply the thermal conductivity, it includes also this effect of the thermal motion. So, you can immediately see that if I were to put the high temperature at the top and the low temperature at the bottom, much of this movement can be completely restricted. That means that the natural convection which will occur because of density changes or density gradients can be reduced or eliminated by using the temperature, high temperature at the top and the low temperature at the bottom. This is in fact the first thing which we are going to do. The second thing is the thickness of the liquid layer. If the thickness of the liquid layer is very small, it also inhibits this natural convection. Therefore, two things I can do. I will take the liquid in the form of a very thin layer, maybe a few millimeters or even less than a millimeter, so that there is not enough chance for this natural convection or the convection motion to set in. And secondly, I am going to put the high temperature at the top and the low temperature at the bottom, and in fact that is what I have shown in the next slide, where I have the main heater here, and because I want to put the high temperature at the top and the low temperature at the bottom, I cannot of course use the symmetric arrangement which we had earlier. If you remember, in the case of solid, I had got two samples, one at the top and one at the bottom, and half the heat went on from the top side and the half from the bottom side. Here I cannot have that facility, because I want to have the high temperature at the top and the low temperature at the bottom. The only way I can do that is to have a single layer of the sample. So I have a single sample layer, and therefore the main heater in this case will have to be backed by a guard heater. So there is a guard heater here and the main heater here. What I will do is I will monitor the temperature difference across these two, and if it is made equal to 0 by suitably controlling the amount of heat I am going to give to the guard heater, then I can assume that all the heat that is generated in the main heater has to go only from the bottom through the liquid layer. Okay. In this case, the guard is doing something different from what was done in the previous case. The previous case, it was trying to make it one dimensional by preventing the heat loss from the lateral side, but here it is actually preventing heat loss from one side altogether, so that there is a purely conductive heat transfer across the layer of the liquid here. And you also know that when liquid gets heated, it tends to expand and the volume changes, and therefore I must allow for the volume changes by having small gallery here, where the excess liquid after it expands will collect in that region. And of course I am going to prevent heat transfer in the lateral direction by having a insulation as is shown in this particular case, and the bottom is cooled by cold water coming in at a low temperature, going out after receiving the heat from the main heater, which passes to the sample, liquid sample, it goes out to this. So the difference between the guarded hot plate apparatus for liquids and solids is very clear. In the case of liquids, I must have only one side heat transfer from one side, that is in the direction of the up and down direction, unlike in the other case where we had both up and down and up, both directions we had. Here we have only one direction, and the main heater is protected or is guarded by the guard heater, which prevents heat transfer from the top altogether. So if the heat transfer is only from one direction, all the heat I am going to give it to the main heater goes through the liquid sample, and if I take a very thin layer of the liquid as is shown here, I can assume one dimensional heat transfer through the liquid, and the same expression which we used earlier is going to be valid for this particular case also. There is another way of doing the whole thing, which is a radial heat flow apparatus, and it is used for both liquids and gases, and let me describe the radial heat flow apparatus. In the other two cases, in the form of slab, either a solid material in the form of a slab or the sample of liquid in the form of a layer, which was a planar layer. In the case of radial heat flow, what I have is a cartridge heater in the form of a cylinder. This is the cartridge heater, which is in the form of a cylinder, and there is an annular region, this thin region here of gap equal to delta. This is a cylinder, and the diameter of the cylinder is d, and there is a narrow gap equal to delta through which heat transfer takes place from the hot plug to the outside. The outside thing, outside the cylinder is actually cooled by cold water coming in as is indicated here and leaving out. Okay. The sample itself is taken in this narrow gap between the inner cylinder and the outer cylinder in the form of an annulus. The sample fluid, either a liquid or gas, has to be filling this narrow gap, and usually the gap is very small. The gap thickness could be sub-millimeter in diameter, maybe 0.5 millimeters or 0.3 millimeters. Therefore, it is very difficult to fill that gap. Therefore, usually the sample fluid is forced through this entrance here by using a syringe or some such method, and then it is made to fill the entire gap. And when either the liquid or the gas comes out from here, we know that the entire thing is filled with the sample liquid or sample gas. Of course, in the case of gas, what we do is we allow the gas whose thermal conductivity we want to measure to freely flow through the system for a certain length of time, so that we know that it has displaced all the other material which was inside, and finally after some time you can expect the gap to be filled with the gas whose thermal conductivity we want to measure. Of course, then you close the entrance and the exit, the two valves which may be there, you close them, and then the gap is now full of the gas whose thermal conductivity I want to measure. Okay. The theory of this is very simple. I have a diameter d which is typically of 25 millimeters or maybe a little more, maybe 40 millimeters, and the thickness of the gap, the gas gap thickness is very small, sub-millimeter. Therefore, we can assume that the layer here is almost like a planar layer, because the area change from inside to the outside is so insignificant. If the diameter is very large compared to the gap, if it is delta is very small compared to capital D, we can assume that the gap is just like a planar layer as far as heat transfer by conduction is concerned. So, I put a thermocouple inside and I put a thermocouple outside. This is the thermocouple pair which is going to measure the temperature difference across the gap between the inner cylinder and outer cylinder. And we also know what is the area for heat transfer, that will be the length of this gap, this annulus length multiplied by pi d. So, that pi d is the circumference multiplied by by length multiplied by this gap thickness, that will give you actually the volume of the sample which is taken here. So, the area will be actually pi d into L, that is the heat transfer area, the gap is delta. So, we can immediately apply the Fourier law of heat conduction and then measure the thermal conductivity. But before we do that, let us just look at the typical numbers. Diameter of the cartridge roughly 25 millimeters, radial clearance 0.3 millimeters, the heat flow area is that pi d into L is about 0.01 square meters, the temperature difference across the gap is roughly of the order of 5 degrees, the heat input can be between 20 and 30 watt depending on the liquid or the gas which you are going to take inside. If it is a gas, the heat transfer will be much lower. If it is a liquid, it could be even 20 to 30 watts of heat which is put in, and the heat is put in the form of electrical heat. The cartridge heater contains an electrical resistance inside, and you measure the heat supplied by the amount of power, electrical power you are going to supply to the heater. So, if you know the heater resistance and the voltage across the leads of the heater, I can find out what is the amount of heat input, and that will be used, that will be exactly equal to the amount of heat which is going through the narrow gap through the sample by conduction plus any losses. The difference between the previous method, where I had a guard to reduce the heat transfer in the or heat losses, and here is that in this particular case the losses are not 0, the losses have to be estimated. If you remember, in the very first slide I said the losses can be reduced or eliminated or estimated and accounted for. So, in the present case what I have to do is to find out what is the loss, and let us look at how I am going to do that. So, suppose I take either a liquid or a gas of known thermal conductivity in this gap. Easiest thing is to take air, you do not have to do anything, air is everywhere, you just allow the entire gap to be filled with air. So, the gap here is full of air, and the thermal conductivity air has been measured by various people, and very accurate values of thermal conductivity are available from the literature. From the tables given in many books on heat transfer, you can find out what is thermal conductivity of air very accurately. So, all I have to do is give different amounts of heat into the heater, give different amounts of heat into the heater, find out by finding out what is the temperature difference across the gap. So, we know the temperature difference across the gap, we also know the thermal conductivity of air at that particular mean temperature. So, you measure the mean temperature between the two, and we know what the thermal conductivity of the air is at that temperature, and therefore, I can find out how much heat is transferred from the inside to the outside by conduction through air. Okay. So, now I will find out this amount, and then I also measure the amount of heat input into the cartridge heater. So, if I take the difference between these two, that will give the loss. So, let me just write it on the board. So, what I am going to do is, so Q through air is estimated based on K of air, delta T, and other geometric parameters. Okay. So, we know that Q through air will be K multiplied by delta T divided by delta, because we are assuming that the radial clearance is very small. So, it is almost like a slab heat transfer through a plane parallel layer. So, K delta T by delta, and if I measure this, if I multiply this by A, I will get Q through air, Q air multiplied by A for the heat transfer area will give you Q air, and Q supplied minus Q air is equal to the loss, we will say L, and this will be a function of delta T, the temperature difference across the gap. So, the theoretical basis is the following: when I have a different sample, not air in that gap, I am assuming that if the temperature difference across the gap is the same as in the case of air experiment, the amount of heat loss is not going to change much. So, the experiment with air whose thermal conductivity is known is going to give me a handle on the problem of heat loss from the system, which will be a function of delta T. So, if I call delta T is theta, this becomes a function of theta, and in fact, I have data for a particular setup in the form of heat loss calibration chart. You can see that as the temperature difference changes from 0.5 to about 10 degrees here, you can see that the loss of the heat due to the heat loss from the system goes from about here to about 3 to 4 watts. Okay. So, suppose I am performing an experiment with a liquid or liquid of unknown thermal conductivity, I find out what is the temperature difference, and then the corresponding value of loss I get from here, and this I subtract from the total amount of heat I am going to supply through the plug, and that will be the actual amount of heat transfer through the liquid which the sample liquid I have taken in the gap between the inner and the outer cylinder. So, I can now find out what is the amount of heat transferred by conduction alone, and then obtain the thermal conductivity. The second point is, because the gap between the two is very small and the delta T is also very small, generally of this order, there is no appreciable movement of the liquid, and therefore I can assume that it is purely conductive heat transfer. We will pursue a problem corresponding to this particular technique in the next lecture.